Alright, so we're going to go ahead and finish up this wave things today with doing standing waves. Okay, and to start with standing waves we need to worry about reflections. So we need to talk about a little bit deeper into the idea of what happens with reflections. And we have two main types of reflections. We can have reflection off what is called a fixed boundary or off what is called a free boundary, and they're going to act a little different. So to show an example of the fixed boundary, let's go ahead and let's just say we have a pole or something like that, and then we have a wave, a string tied to it with a wave on it, and it's fixed to that pole, this rod or whatever it is, such that it can't move. So it's tied right there, it's not allowed to move, and this wave is going in this direction. What's going to happen when it hits and it reflects off? Well, for a fixed boundary, right, let's redraw our pole here, so that's, same pole, it's attached here. When the wave hits it, goes in, hits it, and reflects back, what happens is it reflects inverted. Okay, it inverts. Crests become troughs and troughs become crests. They flip over. All right? For a free boundary, we want to do something similar. We have our pole here, but instead the string is tied loosely around it so that it can actually move up and down itself. And so we have a similar wave pulse coming in, headed in this way. And what will happen is when it hits here, this little knot will go up and come back down, and then it actually sends back the pulse, but this time it's non-inverted. So over here, we end up with an inverted reflection. It's inverted. That's an E. Inverted, and over here, it's non-inverted. Okay? And that's the thing we're most interested in. And actually what we're going to be mostly interested in is this fixed boundary thing. So let's go ahead and make a few definitions here. Let's go ahead and define a few things. First off, damping. This we're going to largely ignore, at least in this video. We're going to largely ignore damping, but this is when energy is lost. Energy lost to the surroundings. So this would be, if you had waves traveling on a string, this would be like, friction and stuff like that, running into air, all that kind of stuff. It's energy lost to the surroundings. The amount of it that's lost really just depends on your situation, and it varies from situation to situation. The next is what we're actually worrying about. Well, actually not, sorry, let's do resonance first. Resonance. This is when a driving frequency, something making the motion, matches the actual natural frequency of the system. So the external driver matches the natural frequency of the system. So the best example I think of with this is when you're on a swing, you're pushing someone on a swing. When they're all the way back and they swing like this, they swing forward and they swing back, and you're standing back here and you're pushing them. Whenever they get here, you're pushing this swing. I guess I could put a person actually on the swing, right? Someone's holding on to the swing there. Whenever you push them, you have to time your pushes. You don't want to push them forward this way while they're still swinging backwards, right? What do? You wait, they swing all the way up, they reach their highest point, and just as they start to go forward, you push them. And then you wait, and they get all the way up here to the highest point, and they just start to go forward, and then you push them. So you're always pushing in the direction they're heading or about to head. If you didn't match your pushes up, right, you're the external driver. If you didn't match your frequency of pushes to the frequency of the swing, you'd mess it all up. So instead of waiting and you push once at the right time and push once at the right time, you're pushing at that same frequency. You can imagine you push them, they got over here, and then they got, like maybe they were right here and they were going back really fast, and then you tried to push them. You'd end up just stopping them. You'd stop the motion. But if you push them at the natural frequency, you can keep pushing them, and so at first they go just a little bit, and then they start swinging higher and higher because you keep matching that frequency. You're the external driver, you match that frequency, and you end up getting them swinging really high by matching the natural frequency of their swing which would be the frequency of their pendulum swing, because they're acting like a pendulum. All right, and that's an example of resonance, when whatever is causing, inputting energy is inputting it at the same frequency that the system wants to go out, and then it will resonate. The next thing is a standing wave. This is a long definition. You might have to just rewind because I'm not going to write this whole thing out. A standing wave, this is when reflected waves cause what is called a stationary wave. It's not really stationary, but it kind of looks like it's stationary. It causes this stationary waveform where the reflected waves are sending energy one way. So you have incoming waves and you have reflected waves, so that there's no net energy transferred through this wave, because one wave is taking energy one way and then it's reflecting back and coming the other way. So there's no net energy transferred. It has fixed locations where there's zero, basically there's zero amplitude, where it's always a destructive interference, and these are called nodes. Kind of goes back to those nodal lines where it was always destructive interference. You'll have these places along the fixed wave where it's always destructive interference and canceling out. And you'll also have fixed locations called antinodes, kind of like the anti-nodal lines, antinodes, where you get the maximum amplitude and you get the maximum constructive interference. And nodes are separated. These nodes, they're separated by half the wavelength. All right, it's going to occur every distance of a half a wavelength if you get this. Okay, and this standing wave occurs when you match a resonance of something like that with a certain frequency put in. So let's go ahead and start trying this with a wave on a string. So let's say we have just a regular old string here, all right? And what we do, it has a length of L, is we start moving this end really slowly. We're going to just slightly vibrate this end. And what's going to happen is we're going to send some little waves down here. We're just going to move it kind of slowly. We're not going to shake it as hard as we can. We're just going to move it slowly. So we want a really, really low frequency. And so waves are going to come in and they're just going to kind of bounce out. And we're going to have this jumbled mess. But if you start slowly increasing your speed from like the slowest possible frequency you could do, and we start getting a little faster and a little faster, what'll happen is you first start off and you're putting like short waves on there like this, and then you put a little bit longer of a wave on there, and then you put a bit longer of a wave on there, and all these waves are reflecting back, and they're reflecting back inverted because we have this end fixed, right? And so eventually what you'll do is you'll find you're putting a wave on there that's exactly twice the wavelength, twice the length of your string. And so what will happen is you send in a crest like this, and then the second half of the wave you still haven't come. So you raised your hand up and you sent in the crest, and in a moment you're going to drop your hand, and the rest of the wave, the trough, is going to go sent on. Okay, so we're at this moment where we've created a wavelength twice the length of the string, and the rest of the crest of the wave is still on its way to come. And then as this crest goes in, it's going to reflect back. And this is off a fixed band rate, so it's going to reflect back as a trough. But it's going to reflect back at a trough, again, same speed, it's going to start coming back. At the same time, you start sending in the second half of the wave, which is a trough, which means you're going to get a trough meeting a trough, and you're going to get a very big displacement. And they're going to add on to each other, and you're going to get this negative displacement. Then the incoming trough's going to go, it's going to bounce back as a crest, just as the returning, the reflected was original crest is now reflected as a trough. It's going to reflect back as a crest, and it's going to reflect back as a crest just as you were bringing your hand up to add another crest in. And so this trough here is going to reflect as a crest, and then the original crest that reflected as a trough is now reflecting as a crest as you put another crest in, and we have all three crests meeting, and we get an even bigger wave. And then all those crests reflect back as troughs as you add another trough, and they all reflect down as troughs, and it gets a little bigger. And then it goes back to a little bigger with now a bunch of crests. They all reflect, all the troughs reflect as crests, and you get crests. And you have crests and troughs and crests and troughs. And the center of this just goes up and down, back and forth like this, kind of like when you do jump rope. except just up and down instead of in a circle. And you get this up and down motion, and you get this what is called a standing wave. At this end, we always have just zero. It's fixed, it never moves, it's a node. Right in the middle where we get this maximum displacement here as it goes up and down in the middle, that's an antinode. And then over here we're not moving it very much. We have to input a little bit of energy, but it's essentially close enough to being just, we call it a node. Okay? And this is what is called our first harmonic. If we have any faster of a frequency, right? Oops, I kind of drew those in reverse. If we have any other kind of a frequency, if we have too long of a wave, then what we have is, like if the wave is longer than the string or longer than twice the string, then we have the crest reflecting back before the next trough comes in, and everything gets out of whack and you just end with a jumbled mess. If it's any shorter than this, we end up with a jumbled mess because the crest hasn't started to reflect when the trough is coming in, and you end up with a crazy jumbled mess. And you can try this. There's a certain frequency you can hit and you get a nice standing wave. Okay? And that's what's called the fundamental harmonic. This is called a harmonic. And this is the fundamental or first. It's the fundamental or first harmonic. Okay, and that's the first one we get. And when we look at that, the wavelength, we get that when the wavelength is equal to 2 times the length of the string. So now we start going faster and faster. So we have our same string, but now we've passed over this frequency. We start going faster and faster, and it becomes a jumbled mess. But eventually you'll reach a point where you get something very nice again. And that point occurs when the wavelength is equal to the length of the string. And what happens is this trough reflects and hits this incoming crest. This is moving this way. This guy reflects back as a crest, and crests meet crests, and then this incoming trough makes a trough here, and then this crest comes over and reflects as a trough, and you end up with crests meeting troughs, and you get something that kind of looks like this. And what's happening is when the left side is up, the right side is down. Then as the right side goes up, the left side goes down, and you end up with this kind of alternating motion. This one's up, this one's down, this one's up, then this one's down. And in the middle, it's always destructive interference. You always have crests meeting troughs, and it's always completely destructive, and it makes a node. And we still have these 2 nodes at the end, but now we have one antinode here and another antinode here, and we basically added in an extra node and antinode there. And this little middle part, you could put your finger right down here. You could put your hand right here, and it isn't going to get hit because in the middle it's always destructive interference and you don't get any movement there. It's like the waves cancel out and then they come right back as it goes back and forth between these. All right? And this is the second harmonic. This is the second harmonic. And with the second harmonic, we have a wavelength equal to L. All right? You can see that here's one full wave right there. And that one full wave is the same length as the string. So let's go to the next one. So now we start speeding up again. Same string, same length L. And we get a jumbled mess again. But eventually, what'll happen is you'll end up with another nice wave. And it'll look like this. This will be up, down, oops, up, down. And then this, we'll do that. So while this side is up, this middle part is down, and this end is up. And then when this end goes down, the middle will go up, and the top, or in the left, sorry, the middle goes up, and the left will go down. So the 2 outer ones are going to always be, when this one's up, this one's up. When the middle is down, these 2 are up. When the middle is up, these 2 are down. So they kind of flip-flop with each other. And this is the third harmonic. Third harmonic. Okay, this was the second harmonic. And look here, we have 1 node, 2 nodes, 3 nodes, 4 nodes. So up here we had 3 nodes, here we had 2 nodes, now we have 4 nodes. So we added an extra node. We had 1 antinode, then 2 antinodes, and now 3 antinodes. 1, 2, 3. And if we look at the wavelength here, we've got lambda equals, what is this? Well, what's one wavelength? Here's one wavelength right there. And if you look at it, it's exactly 2/3 of the wave. Or if you want, we can say that L is 1.5 waves. So L is